Hello friends, welcome to this lecture of data structure and algorithm design. In this lecture, I am going to discuss the concept of asymptotic notation. There are various kinds of the asymptotic notations discussed in data structure and algorithm design. The sole purpose of discussing asymptotic notation is to determine the time complexity of a given algorithm. So let us check what actually the asymptotic notation is. In order to discuss the asymptotic notation, we have certain assumptions to follow. And what are they? Let us discuss them. Let us consider Fn and Gn as two running time for a given algorithm. Of size n, then there are certain assumptions to follow, and the assumptions basically are: number one, Fn and Gn must be non-negative. It is a known fact that running time cannot be expressed in negative terms. So here Fn and Gn must be non-negative. Fn and Gn must be increasing functions. And the value of n must be large. The idea of keeping the value of n large is that when we are going to find the limit value of n for a given function, suppose the function is something like this, then we can evaluate to 0. That means our running time would be get reduced here. So in order to have the reduced running time value, we are going to take the large value of n. So how these assumptions will be useful in determining the time complexities of various algorithms through asymptotic notation, that is the matter to discuss here. So there are various kinds of the asymptotic notations are there, and the important of them are basically various kinds of the asymptotic notations to be discussed. Number one, big O, big omega. This is big O, big omega. Then theta theta, then small o, and small omega. So these are the 5 types of asymptotic notation that we have to discuss here. Fine. So let us begin the discussion with big O, omega. First, we have to consider definition of big O. And the definition of big O simply says that it gives upper bound. It gives upper bound of running time for a given algorithm. And it is represented as, suppose we have considered the two functions f n and gn, then we have to consider the fn and gn in this way. Fine? fn and gn in this manner. So, what is the idea of this? The idea is simple, that big O gives us worst case for a given algorithm. Worst case time for given algorithm. And this can be understood mathematically as that there exists some positive integer say C is a positive integer C and n naught such that fn is always less than equal to gn. It is cg, right? For all n greater than equal to n0. So this is the mathematical derivation of big O. Fine. So we can understand it through graph also. If we draw a graph for big O, then the graph will be followed as suppose here we have the size of a given algorithm and here we have running time. So the graph that we would have for this mathematical definition suppose this is a function cgn and this is a function we have fn. So at beginning fn had higher running time as compared to the cgn, but there would be a certain value of n, let us consider as n naught, from where the running time of cgn keeps increasing and the running time of fn goes to be reduced as compared to the cgn. So we can simply get the idea of this mathematical definition of big. That means for n greater than equal to n, you can see from here the value of cgn keeps increasing and the value of fn is going to be reduced as compared to the cgn for this value. Fine. So that is the idea of the graphical design of this big O asymptotic notation. We can also solve the problem through big O using limit definition. We can also give the limit definition for big O asymptotic notation. And the limit definition says that limit n tends to infinity, if we express the two running time in this fashion, then the value that we are going to obtain for big O asymptotic notation would be either 0 or some finite value. If we are able to obtain the result of limit definition of running time of fn and gn expressed in this manner to be either as 0 or finite, then we are in a position to say that the asymptotic running time for a given algorithm is big O. That means the relation would be followed in this fashion. Fine. So let us take some examples to support all these definitions and discussion. So let us take the first example. If we have one function as 2n and another function gn as 3n, and from these definition we can easily conclude that fn is the order of gn, which implies through mathematical definition we can say fn is less than equal to cgn, and it is clear from the provided function values that 2n is always less than equal to 3n. That means the definition that we considered for fn and gn for big O is correct. So the question would be asked in exam in this way, that if fn is equal to 2n and gn is equal to 3n, would it be justifiable to say that fn is order of gn? The question would be something like that. So it is clear that the value we have for Fn is 2n, and for the for Gn we have the value 3n. Fine. So we can say we can simply observe that it is nothing but 2n less than equal to 3n, and which is totally justifiable. Hence, that this expression is true here. We can also verify this thing through the limit definition also. Fine. If we solve this problem using the limit definition, (2n and 3n), we are in a position to solve it. We can see here that it is 2 by 3, and we can write it in this fashion. And 2 by 3, if we solve it, so what we would obtain, it would be something like 0.66 n, and if we evaluate the limit definition, that means 0.66 raised to the power infinity, and we know that if we evaluated this in infinity as a power over 0.66, we can simply can understand that how small value it would be, and it would be much closer to 0. Fine. So as we had discussed in our definition, that if we obtain the limit value for the two running time as either 0 or finite value, then the definition of the given problem is totally justifiable. That means it is correctly defined here. Fine. So this is how we have to solve the problem related to the big O asymptotic notation. We can take more example, fine, to understand this concept clearly, but we would focus this in our next lecture. Fine.